All right. I tried to do a video on a FET simulation and it did not work very well. So if you guys want to see how this works with single and double slits, one thing, the O Physics site has a couple of simulations that are decent, but the FET simulation allows you to insert both a single and a double slit. So if you want to see how some of this actually functions, just Google FET interference waves and it'll be the first one that shows up and you guys can click on it. But once again, for some reason that simulation is just locking my screen up every single time. I tried like 5 different times to make the video. So anyway, let's go through a practice problem, but quickly let's review some of the terms that we've already learned. I'm not going to do the single slit practice problem right now. I'll throw one of those in later. But for a double slit, okay, so remember, we have our central bright and we have our first order maximus, okay, where the elm in the equation is just 1, 2, 3, 4, and so on, okay? And so the D is the distance between the slits. Theta is this angle, which if we continue and make a right triangle here to here, the theta here and the theta in our right triangle here is approximately the same since the angles are so small. Lambda is the path difference, so this is the wavelength of the light, so this is the path difference that these two make in order to get to M1. Okay? All right, so here's our practice problem. A monochromatic red light, which is 700 nanometers of wavelength, is projected through a double slit. The second order maxima is located at x equals 20 centimeters, and we want the distance between the slits. Okay, so a couple of things here. We've got wavelength and d in this equation. So d is the distance between the slit. But then we also have length to the screen, and we have x here on this side. So M2 is located at a distance of x on this screen as this interference pattern spreads out, okay? And what we're doing is we're trying to solve for this distance between the slits. Okay, so the first thing we need to do is find theta. We've got a length here of 1.5 meters to the screen, and we have x equals 20 centimeters on this side. So the first step is just to find the angle. So we have x is 20, length is 1.5 meters. So if I use the inverse tangent function, I will get 7.59 degrees out of that. That's pretty simple. It's just a simple right triangle. Okay, so the next step then is just plug it into our diffraction equation. So we have d sine of theta equals m times wavelength. So we're solving for d, so we take sine of 7.59 degrees. And for m, we're going to place 2 in here because this is the second order maxima. So remember, the m is just going to be 1, 2, 3, and so on, times the wavelength. So basically, the path difference from this slit to get to the screen, the path length difference is 2 times 700 nanometers. Okay, so that is the distance that they have to travel, or the difference in the distances that they have to travel. So we will find that the distance between the slit is 1.06 to the negative 5th meters. Once again, this is so hard to sketch out. We're sketching it like this, but this is why we can use sine to solve for this instead of tangent. We can approximate those because this distance here is so small. Okay, so we can end up, we can see that the actual distances are very tiny. Okay, the next question you might be asked at some point is how many bright fringes can possibly appear? So this is actually really easy. If we can imagine having a screen that's near infinite length on the opposite side of the double slit, what we're solving for in a question like this is this elm value. We want to know how many possible bright fringes can occur. Now, we know the second bright occurs at 7.59. The third bright will be a little bit further and further and further away. So what we want to do is we want to set the angle on this one equal to 90 so that we can calculate the absolute value for the number of fringes that we could occur. Okay, so if I plug this in, I end up getting an M value of 15.1. Well, we can't have a partial fringe. So what we have to do is round that number down always, don't ever round up. And we can get a maximum of 15 bright fringes that occur. So the other way that I could ask this is how many bright fringes would be on the screen? Well, this tells me that I have 15 brights on the other side of the zeroth fringe. So if we had a screen that was near infinite length on both sides of the zeroth fringe, we could get 30 total brights, but then we have to add in the central maxima as well. So we could actually get 31 total bright fringes on a screen, and that would be the maximum number that we could get with this particular scenario. Okay, that's it. That's really the math behind these. Once again, the math is pretty easy. It's just the conceptual part that's so hard to convey to you guys based on the way I'm having to teach this. So anyway, I'll have the next worksheet posted, and good luck negotiating that one. Okay.